Hello students, I am going to record myself doing all of the diploma exam questions for the most recent release of questions from 2019. So let's begin. I'm going to assume that you've read the question, and so I will just jump into it to save time. Okay, so which of the following statements makes a valid comparison between photosynthesis and cellular respiration? Photosynthesis is exothermic. That is false. It is endothermic. Both photosynthesis and cellular respiration store energy. That's false. Cellular respiration releases energy to your body, so that's exo. The products in the equation for photosynthesis are the reactants in the equation. Yes, they are reverse of each other, so that's going to be the answer. The water in photosynthesis is in liquid, true, while water in cellular respiration is gas. That is false. In a living thing, both are liquid. Your cells have to be, you don't want water coming off as a gas in your cells because that means your cells would be at 100 degrees Celsius or higher. That would be bad. Okay, question number 1, C. Okay, moving on to the next one. Okay, the statements that apply to the forward reaction are, all right, so forward obviously means this. And the net enthalpy has to be this, so 2. The activation energy, that's this part between there and there. That would be a positive value, not a negative value, because we're going up. The net enthalpy, okay, so that means this, my delta H value here. The graph is going up, so it has to be a positive value. So the answer is 2, 3, 5. Perfect. Let's keep going. What's going on here is they want to know the calorimeter that would have the greatest change in temperature would be the one containing enzymes from. So if you remember, we got glucose, and then we have muscle cell enzymes, and then we have glucose being exposed to yeast cell enzymes. But the key here would be the temperature, and which one's going to rise in temperature more is the one that's going to give off the greater amount of energy, which has to be that one. It's exothermic because it's on the product side. So muscle cells have to be that part of the answer. And then they want to know what's the manipulated variable. Well, we're altering or we're manipulating the type of cell. So I would say the type of enzyme, I should say. That answer is B. Perfect. Let's keep going. In a comparison to a reaction pathway without an enzyme, okay, without, the activation energy for the reaction pathway provided by either enzyme will be, okay, so if you don't, an enzyme is like a catalyst. A catalyst will alter a pathway, but it won't change anything in terms of the delta H. It just lowers like activation energy. So the activation energy would be lower. We'll say that. And the delta H value does not change. So the answer here is D. Remember, we don't, the delta H remains unchanged. The catalyst changes that, but it doesn't alter that. Okay, so that's D. All right, so what do we got going here? Okay, so we've got, it's going to be back up to this information. Yeah, 2, 3, and numerical response 2. All right. Okay, what do they want here? They want, what's the molar enthalpy of reaction for glucose? And they've given us all this information here. All right. Well, I always like to just draw myself just a little picture so I can see what's going on. And like I have my glucose here, right? Glucose, it's giving off energy to the water. I can see that my temperature of the water rose. So heat lost equals heat gained. Heat lost by the thing burning, N delta HM, because it's a chemical change for glucose. Can't spell, oh my goodness. Let's learn how to spell. For glucose equals heat gained by the water. Water goes through a temperature change, MC delta T. They want us to solve for delta H. So I'm going to divide by N for glucose. And then I'm going to solve. So I probably need to save myself a bunch of space. I'll move that over. Okay, here we go. So my mass is 100 grams. I'm going to change that to kilograms. So I'm going to move that's 100 grams. I'm going to move my decimal over and make 0.100 kilograms. I'm doing that just because I've done so many of these. You'll see why in a second. 100 kilograms, that takes care of my mass of water. 4.19, I'm going to change this to kilojoules per kilogram degrees Celsius. Kilograms cancel. My temperature change is 10.1 degrees Celsius. Divide that by my mass of glucose, which is 6.50 grams. And this is calling for moles, so I'm going to just cancel my grams. So I'm going to do moles over the molar mass of glucose of 180.18 grams. Grams cancel. Now you can see why I put in the kilojoules here in the kilograms, because now I have kilojoules per mole, which is what they want for an answer. And I calculate that, and I get 117 kilojoules per mole. So this is 117. And they wanted a 3-digit answer, so we're good there. Perfect. Okay, next question. So I can see that I'm going to use this information for the next 3 questions. I see an equation 1 here. I bet you they're going to make me do Hess's law to solve that at some point. I got another equation here. Okay, an enthalpy diagram that could represent equation 2. So I'm focused on this one. First thing I got to look at is I see that this is negative, like it's exothermic because it's on the product side, which means it's a negative, which means the graph has to go down. So it can't be this one, and it can't be this one because those graphs are going up. And then I see delta H is negative. That looks right. Delta H is positive. It's got to be A. That's my answer on that one. Okay. Enthalpy change of 200 kilojoules observed in equation 2. So same equation. What's the mass of CO2? Okay. So first of all, back up to this one. I ask myself, what is this? Is that a temperature change or a chemical change? Well, I see a chemical reaction there. That's a chemical change. So my formula is delta H equals N delta HM. What do they want? They want mass. So I actually like doing this. I know that N is equal to mass over molar mass. So I'm going to just change my formula right now to this. N, or delta H equals N, which is mass over molar mass times by my delta HM. I just substituted N, which is this, for this. Okay. All right. And then I want to solve for mass, which means molar mass has to come up here. Delta HM has to go on the bottom. So mass is equal to delta H divided by delta HM, and molar mass is on the top. All right. So I just go ahead and solve that. So my delta H is actually this number. They've given me that. That's the 200 kilojoules times by my molar mass for what substance? CO2. So I do my calculation on molar mass. That gives me 44.01 grams per mole. And I'm dividing that by delta HM. Now, slight little trick here. I'm going to do some erasing. Look right here. Oh. Look right here. 508.6 is how many kilojoules when I'm dealing with 2 CO2s. So I got to divide that by 2, and that gives me 254.3. So that's the number that goes here. 254.3 kilojoules per mole. And let's see, kilojoules cancel, moles cancel, left with grams. Plug that into my calculator and I get 34.6 grams. So the answer is B. Okay, let's look at the last one. What do they want here? The reactions descriptions apply to equation 1. Okay. Okay, equation 1, CO2 plus H2 makes H. Okay, so CO2 plus H2 makes HCOOH. Is that right? HCOOH, yeah. All right. Now, I just got to do, if I want to know, like, I got to know this, right? What is that delta H? Because I'm not going to know if it's endo or exo until I find out if it's delta H or not, or if the delta H is negative or positive. So how do I solve for delta H here? Well, I got to do Hess's law. So I didn't write out the whole equation there, but it's basically your products minus reactants. You've probably done enough chemistry that you know what I'm going to do here. I look in my data book. Actually, I should go to my data book. Here, I'll do that. Where did I get that number, 425? This is 0. This is negative 393.5. Let me just show you quick. Where am I? So HCOOH, there's where I got my 425. And then carbon dioxide, you almost probably have that one memorized. It's 393.5. Elements have a heat of formation of 0. So I do my products minus reactants. Now, I didn't put in my units or anything, but I think you know what I'm doing. I guess if I need to, I should put those in. But that's negative 31.5. So this reaction is negative 31.5. All right, now let's go solve it. The reaction is obviously exothermic because of the negative. During the reaction, energy is released to the surroundings. True, not absorbed. False. Energy would be on the product side of the equation, so 6, not that. The potential energy of the reactants is greater than the potential energy of the products. Well, just draw a graph quick. Potential energy diagram. It looks like this, right? Reactants here, products here. Because it's exo, the graph has to go down. So the reactants are higher than the products. So the potential energy of the reactants is greater. That's true, not less than. So my answer is 2, 3, 6, 7. Okay. Okay, next one. In equation 1, the molar enthalpy of reaction for H2 is, okay, so molar means kilojoules per mole, per 1 mole. And in equation 1, I can see that I have 3 H2s. So 3 logs on the fire are giving off that much energy. So I got to divide that by 3, and I will get 30.6. So that's this answer, 30.6 decimal. Okay, I might do some erasing here just to clean up the page. We'll see if I need to. Next question. In equation 2, methane contains chemical energy than the reactant, so more or less chemical energy than the reactants. And this originated from, well, that one's always the sun. So this is always the sun. Okay, so let's look at equation 2. So equation 2, I can see that I'm negative. So I always like to draw this graph. This is like the last question. I'm in the middle of a diploma. I'm stressed out, easy to make mistakes. But we know that it's going down because it's a negative 74.6, so the graph has to go down. And I know that here's my reactants, C and 2 H2s, and this is CH4. And I even know this. I even know that this is 0 because these are elements. And I know this is negative 74.6. So, let's read it again. Methane, now it's asking about methane right here. Methane contains less chemical energy because here I have 0 and now I'm negative 74.6. I gave off energy to the surroundings, which means this now has less energy than what these had. Okay? I always think of it like a stick of dynamite too. Imagine a stick of dynamite. Now explode it. It gave off its energy. Whatever its products are have less energy than what it started with because it gave its energy away. Okay, so my answer then has to be A, less, and the sun. Okay, last one. Okay, so they're going to make us do Hess's law. What's the enthalpy change? Now, in case you didn't realize this, I'm just going to go, oops. In case you didn't realize this, I'm just going to go clean this up. Up here, these are actually formation reactions, element, element, compound. So what we have here is element, element, compound, element, 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 compound. What we have here is the heat of formation. In other words, these are the data book numbers, except if you go look in the data book for that one, it's not there. So you wouldn't be able to solve Hess's law with the data book. This one's in the data book. This one's in the data book, but this equation has 2. So in the data book, it'll be half of this. It'll be the 45.9. But this one's not in the data book. So they've really just given us the data book numbers in disguise. Okay? So if they've given us the heats of formation that are in the data book, we should be able to use Hess's law. Now, I'm not going to cheat on this one. I'm going to write out everything. Hess's law is the sum of the sum of moles times by the delta Hm, the heat of formation of the products, minus the sum of moles times by delta Hm, the molar enthalpy of formation formed from its elements of the reactants. All right. So if I have that, I've got to deal with my products first. So let's go do HCN. HCN, here, let me clean this up. HCN's number is, I'm going to clean more of this up. HCN's number is 270.3, but that is for 2. So I'm going to divide that by 2, and I get 135.15. Okay, it asks for molar, right? Kilojoules per 1 mole. So I'm going to put in 1 mole times by my 135.15 kilojoules per mole. Ugh, that's painful. Okay, plus this is an element, so that's 0. So, okay, that's nice. That's shorter. Minus, now let's go to my reactants. Methane. Methane's number is 74.6 for 1. Perfect. So I'm going to go my 1 mole of methane. So 1 mole times by, what is it? Negative 74.6 kilojoules per mole. Plus ammonia. And ammonia's number is 91.8 when there's 2 of them. When I divide that by 2, I get negative 45.9. That's the number that would be in the data book. I think that one is in the data book, ammonia. Anyway, in my equation, I've got 1 mole. So 1 mole, dang, I'm going to run out of room here, times by negative 45.9 kilojoules per mole. Okay, I'm going to squish this in. Kilojoules per mole. Okay, so moles cancel, moles cancel, moles cancel. Close my bracket. Okay. Apple Pencil on the edge of an iPad is hard to operate. Okay, I do the math on that, and I come out to 255.7 kilojoules, which is C. Oof, that took a long time. I can see why we all want to take shortcuts, because that was long. Anyway, that's how you do it properly. Okay, next question. The enthalpy of change associated with that. So, in other words, what is the delta H? So I'm going to have to do Hess's law, which means I have to do this. Oh, back that up. I need to do that formula again. So Hess's law. All right, well, I'll just abbreviate it. Delta H equals products minus reactants. And I have to go find those numbers in the data book, because this calls for the sum of the heat of formation, right? So I might have them circled. Yeah, carbon dioxide is there. Ethanol, glucose. Here we go. I'll start with ethanol. So I have 2 moles of ethanol times by ethanol's heat of formation in the data book, which is negative 277.6 kilojoules per mole, plus 2 CO2s, which is negative 393.5 kilojoules per mole. Oh, I should have moles over here. Subtract 1 glucose, and glucose is negative 1273.3. That's probably why I don't write my units all the time. I always run out of room. Okay, so cancel, 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 cancel. And that gives me an answer of negative 68.9 kilojoules, which would be B. Okay, how do I do the next one? I think I'm going to have to erase all this. Okay, so this is oxidation reduction question. So ethanol is the product of, and then carbon dioxide is the product of. Okay, so I need to assign oxidation numbers. So we know O is a -2. We know H is a +1. 6 and -2 is -12, +12. So this is 0. So the C is 0. +1 -2 +1. That's going to have to make this. I'm at 5 positive, 6 positive, -2 +4. So I need a -4. -2 times 2. That 2. That gives me my -4. And then -2 +4. Okay. Well, let's look at carbon here. Carbon goes from a 0 to a -2. If the number goes down, we've gained electrons, which is reduction. So ethanol is reduced. So C or D. And then this one goes from a 0 to a +4. If the number goes up, we lost electrons, which is oxidation. So CO2 was oxidized. Answer is D. Okay, perfect. Okay, what's next? Of the equations above, the redox reactions are... Okay, so if there's a change in oxidation number, it's redox. So we're just looking for... So I can tell number 1 has to be and number 4 has to be because I've got element, and then compound, +1, -1. So that there's a change in oxidation numbers. My 0 is turning into a -1, 0 is turning... So that has to be. I can also see that here, right? That's an element. Over here, it's in a compound. Oxidation number has changed. Those two have to be it. 2 and 3 I don't know, so now I have to assign oxidation numbers. -2, that's -6, so that's +6. -2 +1. -2 +1 +6. So the sulfur did not change, the H, the O, so there's no change there. No change in oxidation number. Oxidation number. So 2 is out. H is +1 -3 +1 -2 +1. It's got to be a positive 1, so -3 and 4 positive comes out to +1. -2 +1. The N is a -3 and a -3. Nothing else changed. That one's out. So the answer is B, 1 and 4 only. All right, what's this? During the reaction, the hydrogen sulfide is, so that's this. Hydrogen sulfide is the oxidizing agent or reducing agent. All right. Well, I just need to assign oxidation numbers again. So it's asking about hydrogen sulfide. So H is +1, O is -2. And then over here, S is an element, so it's 0. If the number goes from negative, if the number goes up, my analogy is if the rocket gets blasted into the sky, we lose sight of it. If the number goes up, we lost electrons, which means we're oxidized. So this is oxidized, which is the reducing agent. So this is out because it has to be the reducing agent. And we're oxidized, which means this is out. So A. 11 is A. All right, what do we got here? Okay, well, they want to know the oxidizing agents listed from strongest to weakest. So basically, your standard table of reduction half reactions. The trick with any of these is always making sure you know which ones are the OAs and which ones are the RAs. Metal elements, because it says these are metals, are RAs. And metal ions are usually OAs. But we can always just double check and make sure by like assigning oxidation numbers. That's a +2, that's a 0. If the number goes down, that means we gained electrons. That's reduced, therefore, oxidizing agent. So that confirms that these are my oxidizing agents. Okay, so I'll just get rid of all that. If I know that, it's usually not that easy, but if I know that these are my OAs and these are my RAs, this is pretty straightforward. So I know that CO2 positive has to be above ND because this is a spontaneous reaction. If it wasn't spontaneous, it would look like this. So I know that CO2 positive has to be above ND. Then I can sort of fill out the chart if I wanted to. CO becomes CO solid. Oops. It's big. This is ND solid. And ND was, oops. Okay, so I know that reaction's taken care of. Y3 is below ND because it is not spontaneous. So Y3 positive has to be below ND. There's ND there. So Y3 positive plus 3 electrons goes to Y solid. And the last one, SM2 is below Y. So there's Y. So SM2 positive plus 2 goes to SM solid. There. And these are my OAs with my strongest one at the top. So my order is CO at the top, 5, ND2 positive, 6, Y3, 8, SM2, 7. 5, 6, 8, 7. Okay. And then they want to know, last question, which one is a non-spontaneous reaction of the ones listed? Well, let's take a look. Y3 reacting with SM. Y3 is above SM. That's spontaneous, so that can't be it. So that's out. ND2 and Y. ND2 positive and Y. That is spontaneous, so that's out. Next one. ND2 positive and CO solid. There we go. That is non-spontaneous. The OA is below the RA. So that should be our answer. That has to be our answer. But I'm going to double check, or I'm going to check the last one. CO2 positive and SM. CO2 positive, SM. The OA is above the RA, so that is spontaneous. So that's out. So the answer has to be C. Okay, next one. Oxidation number for sulfur. Okay, straight oxidation number question. Should be easy. O is a minus 2. That makes S a plus 4. So that's 4. Minus 2 and 3 is minus 6. So S is plus 6. Let's see. Plus 1 minus 2. That's 2 times 3 is negative 6. 2 plus 1 is plus 2. So this has to be a plus 4. And then I got minus 2. That's minus 8. Plus 1. Dang it. Plus 1. So this is going to have to be plus 6. So 4, 6, 4, 6. Okay, what's this one? Which of the following identifies the lowest whole number coefficients for water and H positive to complete the balanced half reaction? All right, well, first thing I see here is incomplete. So I taught you guys how to balance an incomplete half reaction. You know, the one where you add waters and add hydrogens and all that. So that's what we're going to do here. So let's do oxidation numbers. This is 0. This is minus 2. 2 times 3 is negative 6. It's got to equal negative 1 because of that charge. So this is plus 5. So I'm going from a 0 to a plus 5. If the number goes up, if the rocket gets blasted into the sky, we lose it. We lost 5 electrons. Okay, I can see a bit of an issue coming up right here. We lose 5 electrons per atom because electrons are assigned, or oxidation numbers are assigned on a per atom basis. I've got 2 bromines there, which means I have 2 here. So I've really got 10 electrons total. And I'm losing them, which means I have to put them on this side. All right. So BRs are now balanced with 2. I now balance waters with O's. I've got 2 times 3. I've got 6 O's, which is 6 O's. 6 and 1, right? That's 6 O's, which makes 12 H positives. All right, that looks better. Okay, so what's the answer to this question now? What are they asking? Whole number coefficients for water. So that would have to be 6, so 3 is out. And, oh, and hydrogen. Hydrogen is 12, so it has to be D. Answer's D. Okay, number 14. During a titration, the student would expect to observe increase in acidity. Well, whenever I look at something like that, on this side of the equation, I don't have acid. On this side, I do. So I'm making acid, so it is becoming more acidic. So I would say A. Decrease in volume of solution. Well, I don't know exactly what they mean by that, but if they mean, as I'm doing it, like I have this much liquid in here, and as I do the titration, I'm squirting liquid into the Erlenmeyer flask, so that's going to increase in volume. So I'd say that's out. It's going to decrease in electrical conductivity. Well, ions cause conductivity. I've got more ions there than I do here. There's none there, none there. So I'd say it'd be increasing conductivity and increasing the intensity of the purple color. Well, this is the purple ion. And I have it on this side and I don't have it on that side, so I'm losing purple. So I would decrease that. So the answer is A. Okay, so it looks like a stoichiometry question. Now to do the stoich, I actually, and this is unbalanced, so I'm going to have to balance my equation. Is SO2 in that data book? I'm just going to use oxidation numbers to do this. And I'm going to balance this. Because I'm going to kind of start from scratch to balance it, I'm actually going to ignore water and ignore H, because I know those will appear as I do my work. So I'm going to have, let's make some room here. Sign oxidation numbers, that's -2, so that's +4. -2 +7. -2 is 8. That'll have to be a +6. +2. So it looks like the S is changing. The S is going from a +4 to a +6. So I lost 2 electrons per atom. Got 1 atom, so I lost 2 electrons there. And the Mn is going from a 7 to a 2. If the number goes down, I gained 5 electrons there. So I have to times this one by 5. I'm going to trace it back. I'm actually timesing that by 5. 5 S's. 5 S's. Times that by 2. 2 Mn. 2 Mn. Here I got 4 times 5. I got 20 O's on that side. Here, sorry, I'm just going to write down. I got 20 O's over there. I got 2 and 4 is 8. 2 times 5 is 10. So I've got 18 O's over here. So I need to add 2 waters right there. And then my H's. I've got 4 H's there, so 4H positive on that side. All right, there's my balanced equation. I'm just going to clean that up so that I can do the rest of this. Okay, so there's my balanced equation. All right, now I'm just going to do stoichiometry. So when I do stoic, I got to label my given and required. My required is the concentration of SO2, and I do know my volume of SO2 right there. So volume equals 150 mils. This is my given number. They gave me a concentration of 0.0100 moles per liter of that. And the volume is 31.5 mils. Okay, I've done enough stoic in my life as a chemistry student that I know I start with givens and I work my way through to requireds. So I have 31.5 mils of MnO4 negative times by 0.0100 moles per liter of MnO4 negative times by, I know my next step is required over given. Required is 5 SO2s over 2 MnO4 negatives. Cancel, cancel. Times by, the last number I have is my volume. I need, I got milliliters here. I need to cancel that. So 1 over 150 mils. Cancel, cancel. And now I have moles per liter of SO2. So I do my math, and that comes out to 0.00525 moles per liter, which, if I move my decimal 1, 2, 3, is 5.25 millimoles per liter, which is C. That was a bit of a, that's a long one. All right, this one. This is an example of, well, this is a, it looks like a battery, right? So a battery is a Voltaic cell. The moist paste of an ammonium chloride allows for the flow of, well, I'm going to say the paste is for the ions, whereas the carbon rod is for the electrons. So it's got to be B. Let's just explain how this reaction works. That was kind of an easy one, but let's just explain this. So my half reactions are here. Zinc is throwing away electrons. So the case right there has electrons in it. And then the electrons, I'll just make a wire here. The electrons flow through the case. And the electrons are going this way, right? Electrons are flowing that way. And then the electrons come down here. So electrons start piling up in here. And then the paste, which is in here, the paste grabs those electrons. So the electrons are coming here, and then they don't jump into the paste, but the MnO2 is touching right here, and that's where the electrons, when they touch the MnO2 grabs the electrons. So that's what's going on. Electrons are going like this. Okay. All right, let me just clean that up. So if that's the case, a couple of things we know: loss of electrons, oxidation anode, gain of electrons, reduction cathode. So this is where oxidation is occurring. So this is my anode half reaction. And this is where reduction's occurring. So this is my cathode half. All right, so I know that zinc is anode. And then the cathode is the other one, so the cathode will be the carbon rod. Cathode is this. That's cathode. Cathode. Okay, anode, cathode. Okay. The paste itself isn't the cathode. It has to be the metal pathway right there. All right, let's answer another question. Probably going to have to look at that. I don't know if I should do it this way. It might be too small on your screen. The cathode in the zinc carbon cell, oh, we already know that. The cathode has to be the carbon rod in the middle, because this stuff is the paste. That's for the flow of ions. The cathode is for the flow of electrons. The electrons will flow, oh, we already know that. Electrons flow anode to cathode. So that's out. So 17 is C. All right. And then you want to know the electric potential. So what's the voltage when this... Oh, they want the voltage when the half cell is operating. Okay, well, let's just do this. How should I do this? I'll just copy this down. Okay, my delta H here is unknown. Okay, and then I know my other reaction is the zinc reaction. And I know that voltage. That voltage is... Oh, I put delta H. Oh, my goodness. The E0 net, or the voltage, equals, I don't know. Zinc in our data book is right here. And its voltage is negative 0.76. That's for a reduction equation going this way. If I flip it, which is what I got in this case, it's a positive 0.76. This is positive 0.76 volts. Okay, I know that. And what else do I know here? Oh, I know the net voltage is 1.5. So I'm not even going to write all that. The net voltage is 1.50 volts. So what's the missing voltage? Well, I do a quick subtraction, and this comes out to 0.74 volts. That's positive for the reduction equation, And that's what they were asking. Perfect. So this answer is 0.74. Okay, done. Okay, what's going on here? So the half reaction that occurs at the cathode is... All right, what do we got? Ethanol, person's breath, electric. Oh, this is a breathalyzer. All right. Okay, so they want to know what's the cathode. Well, we got a little issue right here. They're trying to trick you. I don't know if they're trying to trick you. They're trying to test to see if you recognize something right here. Many of you have probably recognized it already, but let's go look at the data book. Okay, so if you look at this data book here, you'll notice something. Here's our 0 cell. The highest voltage is up here, and then we just start going down to 0, and then we start going negative. So there's an order to that table. And if you look at what we've got, the order is upside down. This one should be up above. Okay, so I'm going to just put it there. I know I could think my way through it without writing it there, but I don't like doing that because I always feel like I'm going to make a mistake. So in my data book, that's the order. And really what's happening here, right? You guys know this. O2 and the 4H positives. That's my oxidizing agent reacting with the ethanol in the breath, alcoholic breath, is the reducing agent. So that's what's happening. So the half reaction that occurs at the cathode is, well, oxidizing agents are reduced, gain of electrons, reduction, cathode. So this is my cathode reaction, which has to be B. Okay, what's next here? Oh, a reference cell question. If the reference cell were changed from hydrogen to cadmium, what's the reduction potential of equation 1? So what does this new voltage become? Let's clean this up. So what does that become for equation 1? Okay, well, let's look at the data book again. What they're saying is... This is called the reference cell, right? The hydrogen half cell. And that's 0. So they're saying, oh no, I can't remember. They're saying that cadmium is the new reference cell. So where the heck is cadmium? There's cadmium. So this becomes 0. Now, what I tell you guys, my students, is the difference between any two is always the same. So if the difference is 0.4 and everything above 0 is positive, if that's 0, this one, the new hydrogen, has to be 0.40 positive. Okay, and now they wanted to know what happens with equation 1, which is 0.58. Right now it's 0.58. So maybe it's better if I show it to you. Let me go back here. Okay, so right now I know that CH3COOH is, right now it's positive 0.58. Hydrogen is 0. Cadmium is negative 0.40. So they said this is now 0. So this one becomes 0.40 because the difference between any two is always the same. If this difference is 0.4, the other difference is 0.4. So now to figure out what's missing here, I have to add 0.58 to this one, which brings my new number to a positive 0.98. And that's my answer. So that has to be D. Okay. Okay, the next one, if a 4 amp If 4.00 times 10 negative 3 amp is maintained for 10 seconds. Yeah, okay, so this is a Faraday law question. And they want mass of ethanol. So what I tell my students is start with the unit you want and put it on top. So I figure out the molar mass of ethanol, and it is 46.08 grams per mole. And notice, I want to keep grams. That's what I want for my answer. So I'm just going to cancel everything else that's not a gram. And the first way to cancel moles is the Faraday constant inverted. So moles of electrons over 9.65 times 10 to the 4th coulombs. Moles are gone. And then I could cancel coulombs with this number. So 4.00 times 10 to the negative 3 amps is the same coulombs per second. Coulombs are gone. Next, let's cancel electrons. I'll just change this to blue. If you look up here, I have 4 electrons for every 1 ethanol. And so I'm going to put electrons on the bottom because they need to cancel. Cancel, cancel. 4 electrons for every 1 ethanol, sorry. Okay, now if you look at units here, I've got grams of ethanol. I want to keep those, keep canceling other things. Next thing I have to cancel is seconds, and they gave me, that's nice, 10.0 seconds, which is over a 1. I think that's everything, because now seconds are gone on my no leftovers. Okay, I punch that into the calculator, and I get 4.78 times 10 to the negative 6 in that format. So 4, 7, 8, 6. Okay, that's it for that one. Okay, so which row identifies one characteristic of a Voltaic cell and of Okay, so I'm looking for 2 trues in the same row. All right. So the voltage of the cell is less than 0. That is false. In Voltaic cells, they have positive voltages. Electrolytic cells have a spontaneous reaction. No, they have a non-spontaneous reaction. A is out. That's a bad one. They're both wrong. Next one. Converts chemical energy to electrical energy. That's true. Voltaic cells take the chemicals and make electricity. Anions towards the cathode. No, anions are always towards the anode in both cells. So that one's at least half right. Moves electrons towards the anode. Electrons always move anode to cathode toward. Nope. Reduces the strongest oxidizing agent at the anode. Gain of electrons, reduction cathode. Loss of electrons, oxidation anode. That one's false. Whew, that's bad. Requires a type of salt bridge? Yes. Requires an external power source? Yes. Electrolytic cells require a power supply. All right. D. Next. The half reaction for hydroxide. Okay, so this is electrolysis. Oh, that was ugly. This is electrolysis. What do we got? Silver, sunken treasure, silver sulfide. Okay, so silver sulfide with NaOH in a non-spontaneous reaction. All right, let's go find those. So they want to know what's happening to OH. What's the reaction? Okay, let's go look at the data book. Silver sulfide is right there. That's tarnish on silver. Hydroxide. Where is hydroxide? There's one there, but we don't have Cl negative present. Oh, there it is. Let's go back right there. So this is electrolysis. So it's a non-spontaneous reaction. That's our OA. That's our RA. So they wanted to know about the hydroxide reaction. Well, reducing agents are oxidized. And so I would have to, right now written this way, the forward way, like that way, the electrons are on this side, which means reduction. So I've got to just flip that. So that's my answer to that question. I flip that, which will be, you know what I just thought of? I could probably take a picture. Whoa, what am I in here? So that one has to be this one flipped. You know what I'm going to do? I'm going to just do a quick experiment here. Live experiment. Copy. All right, kids, let's see. Hey, yeah, look at that. Okay, did I get it right? So let me just clean this all up now. That reaction flipped around. 4 OHs, 2 H2Os. Yep, there it is. 21 is A. Okay, let's go look at the next one. 22. Which of the metals will act spontaneously as reducing agents with silver iodide, but not with silver sulfide? Okay. Those kinds of questions require us to look at the data book. And what I'm going to do, I'm going to use my new skill. Paste. Okay, there's my question. I'm going to clean all these off. Which of the following metals will act spontaneously as reducing agents with silver iodide but not silver sulfide? Okay. So here is silver sulfide. There is silver iodide. And let's go through and find all these guys. So first one, Cu solid is here. Hg liquid is, where are you? Hg liquid right there. Okay. So which of the following metals will act spontaneously as reducing agents? So these are my OAs, right? These are my RAs. Those are certainly not going to be spontaneous. Those are non-spontaneous. They are below, or sorry, they are above. So I'll just get rid of those. All right. Cr and Al. Chromium is right there, and aluminum is right there. So they react spontaneously with both of those. So that's not the answer. Next one, nickel and cobalt. There's nickel, and there's cobalt. All right, this is probably the answer. Which of the following metals will act spontaneously as reducing agents for silver iodide? Okay, those are spontaneous with that one, but not silver sulfide. So that has to be the answer. And gold is way up here, non-spontaneous with both. And magnesium is, where's magnesium? Is right there, which is spontaneous for both. So C has to be the answer. All right. Okay, moving on to the next one. Oh, we're in organic now. So the parent chain is, well, the trick on these is always, you have a tendency to think that's parent, branch, branch, branch. But, of course, the longest continuous chain is the parent. So that looks like that's 3, 4, 5, 6. That's 9. So 23 is A. Non-ane is the parent. Next one. Herbicide 2,4-D is a, well, it's got benzene. As soon as it's got benzene, it's got to be aromatic. and it has a ester or carboxylic acid. Double bond to O, single bond to OH is a carboxylic acid. So straight knowledge question there. It's nice and quick. Let's go to the next one. I like organic. It goes quick. Feels like you're making progress on your diploma. Okay, match the numbers of 2 of the organic compounds listed above. Match 2 of them. Okay, there's going to be lots of different answers on this one then. So, octane is used for fuel in automobiles. So 1, 5. Methane is natural gas, a fuel used in your house, in your furnace. So 2, 7. That's pretty easy. 1, 5, 2, 7. Now there could be lots of other answers too, like methanol is used as antifreeze, you know, for like ethylene glycol or automobile coolant in an automobile, antifreeze. So you could have 3 and 8. It looks like there could be lots of answers here. I'm just curious. Where's our answers? What number was that again? Is that NR9? Yeah, NR9. Okay, lots of answers. You need an algorithm to figure that out. Okay, whatever. Okay. So that's good. We're done that page. Okay, what do we got here? Which of the following conclusions is a valid interpretation of the data above? Boiling point decreases as branches increase. Okay, well, I can see that I've got a straight chain with a bromine, straight chain, and then bromine is not on the end. Here's my parent branch. Okay, so between this one and this one, as I gained a branch, my boiling point went down. Same here. As I gained a branch, my boiling point went from 117 to 80. So that looks like the answer. Let's just go through the others and disprove the others. Boiling point increases as the length of the parent decreases. Well, here's our parent. 1, 2, 3, 4. 1, 2, 3. And the boiling point went down as the chain decreased. So this says the boiling point increases. That's false. It actually decreases as the parent chain decreases. Same here. 4 carbons, 3 carbon parent. So that's false. Out. Okay, next one. Boiling point decreases as the number of carbon atoms increases. Well, it's the same number of carbon atoms on all of these, right? So that can't be true. 1, 2, 3, 4. Like 1, 2, 3, 4. Yeah, so that's out. And boiling point increases as functional groups become less polar. Well, that's not true either, because take a look at this. There's my functional groups, those BRs, these OHs. These are higher boiling points, so they are more polar. These ones up here would be less polar. So does the boiling point increase as we become less polar? No. The boiling point decreases as we become less polar. Okay, so that's that answer. 25 is A. Let's look at 26. Clean that up. 26. Do I need to look up there? Let's find out. Actually, okay, compound 2 can form when butene reacts with... Okay, well, let's do this. Let's just bring compound 2 down here. Copy. Paste. Okay, so we're making that compound. Compound 2 can form when but2-ene reacts with. Okay, so let's draw but2-ene. 1, 2. There's but2-ene. That would react with. Put it up here. Yeah, it looks like we're going to react with HBr. Yeah, so here's what will happen. Oh, I'm going to change one thing here. I'm going to put those dashes on the bottom so you can see what happens. Okay, so this is simply going to react right here, right? This is going to get added right in there. That double bond will snap. That'll form. And that's an addition reaction. And then it'll look just like, then it'll look just like this one. So my double bond snaps, disappears, this bond breaks, and then I get my bond there and there, which is that. So this is HBr in an addition reaction. Answer is D. Okay, let's go to the last one. Using solubility data in the table, arrange the organic compounds in decreasing solubility. So least soluble here, most here. All right. I'll clean all this up. Okay. Well, let's look at the pattern on here. I'm going to just copy this and put it above there. Copy. Let's put it right here. So now we can see it and work with it here. Okay. All right. Well, look, we notice with solubility here. All of these, the BRs, are not soluble. So that has to be the least. So number 2 is the least soluble. Okay, good. And then what I notice here is when OH is on the end, it has the highest boiling point. When OH has been moved to the middle, it has like our, or sorry, it's, I didn't mean boiling point. I meant it's soluble. When OH is moved from the end to inside, it's a little bit more. And when we have a parent branch and an OH in the middle, it's the most. So here's the most. We got OH on the inside. We've got a branch. That has to be the most. That will be 3, most soluble. OH on the inside is second, 3, 1. And then OH is on the end, 4. So 3, 1, 4, 2. Okay, that's it. Okay, next one. So they give us C10H16. It's not an isomer of, oh, well, okay, I'm going to start with this one. And I'll draw it, and I'll see what comes out here. So I got 1, 2, 3, 4, 5, 6, 7. Okay. 8. 1, 2, 3. Yeah, that's always tricky when that straight line comes out of that triple bond. Okay, so this, remember there can only be 4 dashes around a carbon. 4 bonds. 1, 2, 1, 2, 1, 2, 3. Okay. So let's see what we've got. I'll do this in blue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is C10. H1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16. This is C10, H16. So that is an isomer. All right, so I got to keep going. It might be, line diagrams are easy to draw. They're not easy to see the H's. I can maybe speed this up though. I know I got to have like 1, 2, 3, 4, right? So every carbon needs to have 4 dashes. So 2. This is a little tricky here. I've already got 1. I got 1 there, 1 there, 1 there. So I need 1 sticking out there. But so I don't get confused, I'm just going to put this in. 1, 1, 2, 3. That's 4. I need a 1 coming off here. 1, 1, 2, 1, 2. Okay, let's count carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C10. H is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. C10, H. I must have missed one somewhere. That doesn't seem right. Oh, right there. I didn't put. Let's make sure. 1, 2, 3, 4, 5, 6, 7. It's going to get confusing. I got too many blue dots. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Ugh. That's an isomer. Did they make it the last one? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, that's probably it. C10, H14. I think it's C. 1, 1, 1, 1, 1, 2. 2, 3. 1 has to stick out of there. 1, 2, 1, 2, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's an isomer. It's got to be C. Okay, what do we need to know here? The number of carbon-carbon double bonds in that compound, myrcene, is, well, let's draw it. So I'm just going to try to draw C10H16 until I only have 16 H's. So I'm just going to make up where my double bonds go because it can't be all single bonded. I'm betting there's 3. 2, 1, 2, 1, 1, 1, 2, 1, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's C10. Let's make sure my H's are right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so looks like I have 1, 2, 3 double bonds. All right, I didn't think that was going to take as long as that did. Oops. All right, let's see what we got next here. Okay, propane can be recovered from, well, propane comes from crude oil, so I would put a 3 there. We take crude oil, we put it through a fractional distillation tower by the process numbered, 5 fractional distillation. Propane reacts with chlorine gas. Okay, so I could draw propane like this. Chlorine, Cl, Cl. And you can see what's going to happen here, right? We'll replace an H with a Cl. And we'll make plus HCl, and there will be a chlorine sticking off right there. Okay, so propane reacts with chlorine gas in the presence of in a type of reaction numbered. It has to be a substitution reaction. So, because I'm not, yeah, it has to be substitution. 8. It's not an addition reaction. Elimination, I would have formed a double bond if I had have eliminated, so. And hydrogen chloride gas and the organic material numbered. So I made this, and then I made this, which is 1-chloropropane, not ene. So 3581. Okay. Next. Ethyl propanoate can be formed. Okay, so this is your classic ester question, right? That's an ester. If I was to ethyl propanoate, okay, so 1, 2, 3, double bond to O, single bond to O, then ethyl. So there's my ester, and this part used to be ethanol. An OH somewhere. And the other part, this used to be a carboxylic acid. O, single bond to OH. So it was made of propanoic acid and ethanol. That one and that one. If you want to see what the reaction was, the OH comes off of there. The H comes off of this one. They go make water. And then this guy gets pulled down over to here, and that's what this is. Anyway, there you go. I could probably do that a little bit nicer, but I think you guys have, if you're in Chem 30, you probably know that reaction pretty well, ester. Okay. All right, next one. They give us that. Which of the following is not an indication that it's hit equilibrium? All right. Well, constant mass, pressure, temperature. So there's the 5 conditions of equilibrium, right? You got to have a constant temperature, constant pressure. I think that means like a constant number of gas molecules means this is a closed system. We're not changing the number of particles in there. So the only one that's out is this one. 30 is A. Okay, what's next here? When applied to the equilibrium above, the stresses that would shift towards reactants. Okay, well, let's go through them. If I added H2, add H2, that goes up. We shift away, so that would shift towards reactants. So 1. I'll delete those so we can see new every time. If we added CO2, we would shift to the products. If we add a substance, we shift away from what was added. So that's out. If you add a catalyst, catalysts do not affect. Remove CO. If I remove CO, here's what will happen. If I remove CO, I shift to replace what was removed. So that goes to the products. So that's out. Okay. If I removed CH4, okay, if we lose that, we shift to replace. So that shifts towards the reactants. So that one's in. Decrease the volume of the container. So what they want you to do here is think in your mind, if you're decreasing the volume, imagine a syringe and you've got the plunger, right? And so this is space in there. If I push this plunger down, I'm decreasing the volume. Now I got a very small volume in there. If I'm decreasing the volume, I am increasing pressure. When you increase the pressure, it favors the side with the fewest moles. Fewest moles, I've got 1, 2, 2, 4. So yes, that would shift to reactants. 1, 5, and 6. 6. Okay, and it looks like I'm going to use this to answer the questions on the next page as well. So I wonder, for your sake, it might be easier if I just take a snippet of that. All right. Which of the following sketches best represents the progress of the system at equilibrium? Okay, so I'm putting 1 mole, Kc. Well, that's a big number. 3.3 times 10 to the 10. Okay. Okay, well, like, remember when I used those Lego blocks at class? I'm starting with 1 moles per liter of that, 1 moles per liter of that. These are at 0, there's nothing there. Then the reaction has to start, and so these go down, down. As we build these, they go up, right? So I need CO2 and CH4 to go down. CO2, CH4 goes down, goes down. Oh, they all go down. Okay. All right, so that's not helping me. CO and H2 have to go up. Okay. Yeah, okay. All right, well, that's not helping me. Okay, so what else? Just delete that. Let me think here. Oh, this favors products. So my products, because it's, remember, if that number is greater than 0, if that number is greater than 1, it favors products. And the larger it is, the more it's favored. So I need products to be higher than reactants. So this graph is out because my products are not higher. Okay. And because it's such a big number, the gap is huge. So I will say this is D. Yeah, that's right. All right. Now, in order to calculate the equilibrium concentrations, all right, so we're going to need an ice table where X represents the change in nature. Oh. Okay, so they want us to know which one of these is correct. Okay, well, you know what I'm going to do? I'm going to just drag this down here now. There, I don't have to write it out. Get rid of all those. Okay. Well, to save space here. So I'm going to need an ice table. Ice. I know this was 1 and 1. Don't worry about that. These are zeros to begin with. And then they said, they say X is CH4, the change in CH4. That's what the C stands for, change. So let X equal the change. Now, I don't know how much of this you remember, but in order to go from this to these, you have to times it by required over given. Okay, so I don't really want to take the time to explain this, but I will. If I have X CH4s, I got to times it by required over given. So let's say I'm trying to find that spot. My required is this one, and this is my given. I have 2 COs over 1 CH4. CH4 cancels, right? So now I have 2x. I've got 2 times x. So I can see here that I have a 1-to-1 ratio. That's x. But on this side, this is 2x, 2x. Okay, all right. So if we have that in place, delete that. Now I can see that this is 1.0 minus x and 1.0 minus x. And this is 2x and 2x. Remember, these go down, so I'm minusing x. These are going up, right, as a reaction happens, so I'm adding. Okay, and then I say my Kc equals products over reactants. All right, I'll save myself room. And then my products are those guys. And yeah, they wanted equilibrium concentrations. That's why I'm using those numbers, E. So I have 2x. So this is 2x, and coefficients become exponents. 2x squared. And then I have another one of those. Well, that could get really confusing. Holy. 2x squared, because that one's coefficient becomes exponent. And on the other side, I have 1.0 minus x, and that happens twice. Like I have 1.0 minus x here, 1.0 minus x, so that's squared. And we can ignore minus x eventually and all that, right? But looks like my answer is B. 3.3 times 10 to the negative 10, which they gave us, equals 2x squared, 1.0x. Yeah, B. Sheesh, this is a long one. Okay, number 33. The value of the equilibrium constant is, okay, so they gave us these. So what I'm looking for is, do I need an ice table here? Nope, it's at equilibrium. So I can just plug it in. So Kc equals products over reactants. Products. The concentration of CH3OH divided by my reactants, concentration of CO and H2, H2. Coefficient becomes exponent. So this is 2.75 over CO, 0.75, and H2, 1.25 squared. Do that on my calculator, and I get 2.346. 2.3. Answer is C. All right, heating the equilibrium system represented by the equation above would shift the equilibrium towards, okay, so if I heated it up, where would it go? Okay, so I'm going to just get rid of this. Well, I can see this, right? I can see that that is a negative, which means exo, so kilojoules is over here. If I heat this up, we shift away from the heat. So I would shift towards reactants. And if I did that, these numbers would be going up, right? Those are going up. And these numbers are actually going down. I'll show it like this. I'll show lots of dots there. And then I'm actually starting to, as they go down, there's less of those, which means my numerator, this number, is going down, and my denominator is going up. So that is going to end up decreasing the value of Kc. And you know what? You're in the test. You're thinking your way through it. You can even make up some numbers here. I do this all the time. So watch this. I'm going to just say take my 2.75. I'll just make that smaller because that's going down. So I'll just make up a number there quick. These numbers are going up. So let's just put in a 0.95. We're just guessing. We're making it up here, but 1.25 becomes 1.5. Do the math on that. 1.169. That answer, that's decreasing. So 34 is B. Perfect. Okay, what do we got here? So they give us an equilibrium equation. Initially, we have 0.18, 0.13. Equilibrium is established. Okay, so ice table. Okay, well, let's do it. So I'm going to just use this equation up here. I'm just going to use that I'm going to just pretend that's right here. So ice table, CS2 is 0.18, like this is 0.18. H2 is right here, that's 0.31. What else did they tell us? These are 0. When equilibrium is reached, CS2, this one is 0.13. Okay. What do they want to know? The concentration of hydrogen gas at equilibrium. Oh, okay, so they just want to know what's this number. Okay, so we're going to try to find that number. So if I have my initial number, the 0.18 and the 0.13, I can just subtract those and I get 0.05. And then I'm going to convert this number over to that number by using required over given. So I'm going to take 0.05 CS2 times by required over given. Required for H2s given a CS2, cancel. So 0.05 times 4 gives me 0.20. So that is what goes here. And then I subtract those, and I get 0.11. And that is my answer, 0.11. Okay, number 35. What do they want here? H2BO3 negative would form a conjugate acid-base pair with 3 or 1 and 3. All right. Well, if I take this one, a conjugate pair differs by 1 proton, 1 H. So this one differs from that one by 1 H, H3 to H2. And it also differs from that one, H2 to H1. So the answer has to be C or D. And the amphiprotic species are, well, amphiprotic means, let's just clean this up again. Amphiprotic means it can act as an acid or a base. It can throw away an H. It can receive an H positive. So This one can't receive an H because it doesn't have a negative. It needs to have a negative to receive an H positive. So that's out. This one has an H, so it can throw one away. Has a negative, so it can receive an H positive. Same with this one. So 2 and 3 work. This one can receive, but it doesn't have any H's to give, so that's out. So the answer has to be D. Perfect. Okay, what do we got going on here? So they want to know which of the following rows identifies observed color, effect on pH, after a small amount of HCl is added. All right. So I got a solution 1 with H2S, solution 2 with H2S. Okay. This is before adding, this is after. All right. Well, you've probably spotted this is a buffer. And a buffer resists a change in pH. Now I do need to figure out chlorophenol red. Okay. Chlorophenol red. I might as well just copy this since I now have that skill set. Copy. Okay, so here's solution 1. We'll do solution 2 here. When I add acid to this one, to solution 1, it's not a buffer. So the pH is going to drop. When I add acid to this one, it's a buffer, so the pH is going to be relatively stable. So if both solutions are orange right now, do I have orange? How do I change colors on this thing? Orange, yeah. Okay, both solutions are orange right now. Okay. If I add acid, this one, solution 1, is going to go into the yellow range because the pH is going to start dropping. And so this one will turn yellow. It doesn't get rid of the... Let's see what happens if I do this. Yeah. This one's going to turn yellow, right? So this one's going to turn yellow. And the pH is going to go lower than 6.6. It's going to start dropping. Oh, that's not what I want. I'm taking too much time playing with tools here. And the other one is going to stay orange because it will resist a change in pH. Even though I'm pouring acid in, the buffer will resist that change in pH. So this one will remain orange. Okay, well, let's find the graph or the answer for this then. So solution 1 will turn yellow. Well, that means this has to be the answer. Well, it didn't. Anyway, let's look at the other one. And the other one will turn orange. And there won't be a change in the pH. Yeah, okay. So 36 is C. Okay, got to play with the tools though. Okay, this page wants us to do these 3. Okay. You want us to calculate Kb for sorbic acid. Sorbic acid is this. All right. Okay. Ka. All right. Okay, well, they gave us the Kb, right? So Ka times Kb equals Kw, which is a constant. So if I want to find Ka, I'm simply going to divide by Kb. 1.00 times 10 to the negative 14 moles per liter squared divided by Kb times 10 to the negative 10 equals 1.7 times 10 to the negative 5. which means I want, what do they want here? Oh, 3-digit answer, so 175. The amount of sorbic acid present could be increased by. So sorbic acid is this guy. Yeah. All right. Well, if I added HCl, what I'm adding is H positives, right? Acids. So H positives, OH negatives kill each other, neutralize each other, so that goes down. So that would shift to replace, and that would go up. So that would make sorbic acid go up. So the answer should be A. Let's just go through the rest of them. If I added NaOH, I'd be adding OH negative up. So that would shift away, meaning sorbic acid would go down. That's out. If I remove water, same thing. I'm going to shift that way. That didn't look very good. I'm going to shift that way. So that's out. Same thing if I remove this, I'm going to shift that way again. So that's out. Okay, good. Let's see. When reacting this, an acid that would produce an equilibrium that favors reactants. Okay, so remember, when acid is below base, reactants are favored. Maybe one thing here you'd have to realize is the K breaks off, and this is C5H7COO negative, right? So that's my base. Now I'm going to go find which acid produces equilibrium that favors this side. So we got to go to the data book. Okay, they gave us HCOOH. They gave us that. C2H5OCOOH. They gave us that one. C6H5COOH. That one. And C2H5COOH. Where's that? C2H5. Okay, now I bet the one that I want isn't on here. C5. Yeah, it's not on there. Okay, I gotta go back here. Well, I know this, right? The Ka is 1.7 times 10 to the negative 5. 1.7. Yeah, right there. Okay. So my C7, what the heck was it? C5H7 COO negative goes right there. So there it is. When that acid is below that base, it will favor reactants. So the answer is C2H5COOH. C2H5. That one, C. Okay, that's how you figure that one out. Okay, we're on the home stretch here. Let's see if we can get this test done. Sorbic acid is classified as saturated or unsaturated, and the rate of its reaction with bromine is predicted to be fast or slow. All right. Okay, well, I see double bonds, which means unsaturated. So it's got to be C or D. And bromine reacts with double bonds. Like if you have, how many do I got here? 1, 2, 3, 4, 5, 6. It's too big. Anyway, my whole point here is, oh, that can't be there. Make this a little smaller so we can be accurate. Okay. Double bond to O, single bond to my OH. Okay. So the way bromine reacts here, bromine can react with a, I'll put these on the bottom and then we can show it. Bromine could come in and react right here. That bond snaps And then bromines can stick right there, which is called an addition reaction. Okay. So that happens. To my knowledge, the rate of reaction isn't really in our course. I'd have to go look, and I don't think that's in our course. But it happens pretty fast, so I would say this is C. 40. Compound 1 can be produced from sorbic acid in, what's compound 1 again? Compound 1. Oh yeah, that's kind of what I just showed. So notice here, let me clean this up. Look at the difference. Here I have a double bond. That bond is gone, and I didn't add BRs to it. I added hydrogens. Anyway, so that was an addition reaction. I just added hydrogens. And compound 2 can be produced from sorbic acid in, so compound 2 is an ester, double bond to O, single bond to O. Okay, so 40 is A. Okay, what's going on here? In the reaction above, Bronsted-Lowry acids are. Okay, well that should be easy. So I can see that water is becoming OH negative, so water is throwing away its H. So that's the acid. So water is acid. This is base. And on this side, the H is jumping on if we're going that way, which makes this conjugate acid, conjugate base. So my bases are water, or my acids are water, and that one, 41 is B. 42. Oh, looks like ice question. So they want to know what's the OH negative concentration. All right, well, let's do this. Copy. Let's make that a little bigger. All right, let's do an ice table. Don't worry about water. Concentration's too massive. So this is a 0.100 moles per liter solution. These are zeros. They didn't give me anything else other than the KB. KB matches OH negative. Let X equal the change. All of these are 1 to 1. So it's X's everywhere. This is 0.100 minus X. In our course, we can ignore minus X. I take my KB, 1.62 times 10 to the negative 6 equals X squared, products over reactants, 0.100. And that gives me, if I use my calculator properly, 4.02 times 10 to the negative 4. So that's what X is, which means that's what that is. 4 points, so that should be B. Oh, I like it when they give me quick questions at the end of a test. Okay, so match the species above with their descriptions below. All right. So those are some of them. Looks like they have H's and they have negatives. Like you've been on both sides of the chart. They want to know about polyprotic, conjugate base. Okay. So hopefully these are all on the chart, because then if they are, makes this a little easier to look at for you guys. Get rid of all of this. Okay, let's go through, find this. Species that is both polyprotic and amphiprotic. So let's go find this one. This can't be it because it's only going to be on that side. It doesn't have a negative, right? So that can't be it. But this one will be here, and it should be on the other side as well, right there. And then that one will form this one. What is that? Oh yeah, that's down here too. Okay, so the answer here is, looks like there could be a couple of answers here. This one and this one are amphiprotic, which means that is number 2. And this one and this one are amphiprotic. Oh, it says polyprotic and amphiprotic. Oh, okay. Yeah, okay. So those are both amphiprotic, and they're both polyprotic as well. They have more than one. Well, you could argue they have more than one proton. Like this, where did that H come from? So this H left, going there. Oh yeah, so there's multiple H's going on in here. How can I show this to you? We've got a couple of H's there, right? There's still an H. So both of those would work. So I could put 2 or 3 here. 2 or 3. Okay, the species that is the conjugate base of this So that means that is going to act as an acid right there. That's the acid. Its conjugate base is this guy, which is number 3. Right there. Okay, next one. Species with the weakest conjugate base. Well, strongest base is down here, so therefore the weakest base is this guy, which is number 1. Oh wait. Oh yeah, the species with, yeah, this guy's conjugate base is the weakest. Yeah, so that's 1. Species that will form a buffer when mixed with an equal amount of C3H5. So, erase these. So this, when mixed with this, a buffer differs by 1 proton, will create a buffer. So that and that will make a buffer. So it's this guy that would make our buffer. Okay, there's that question. Limestone rocks, buffer. We drop acid on that buffer. What's the reaction? Okay, so which reaction? Okay. The effect of the buffer is to, well, it's got to be to maintain. So it's got to be, it's got to be A or C. Okay, so that's the one I'm looking for. Okay, so what I'm going to do is I'm going to clean this up. Let's do this again. Let's copy this. Okay, and I'm going to paste. All right. Okay, there's my question. So let's go find our buffer first of all. There's our buffer down here, HCO3 negative and CO3 negative. And then if I added acid to it, I'll do this. I have to make this smaller. Here's my acid, right? So the acid will react with the base. So H3O positive will react with CO3 negative and maintain. Answer is A. Okay, that's A, and this was 3, 3, 1, 2. This could have been a 2. All right, 2 more questions. Let's go. Rain is collected, pH is 5.4. The OH Okay, they want to know the OH. Well, okay, so that's the trick, right? You got pH, but they want to know what's the OH. Okay, so if my pH equals 5.400, my pOH is 14 minus that number, which is 8.600. And then if I want to find the concentration of OH negative, I go 10 to the negative pOH. So I put in 10 to the negative on my calculator, and I will get 2.51 times 10 to the negative 9, and they want 2519. 2519. Okay. And the last question of this diploma. Titrant added to the solution is, so what's the titrant? And the sample is mono or poly. Okay. Well, I always like to just be careful. Draw my barrette. Draw a flask. If I'm starting up here, base is in my flask. So I am dropping acid. I'm dropping acid into my base. Okay, so didn't mean to bring any drug-related humor in there. Sorry, people. Okay, in the titration represented by the graph above, the titrant that is added to the solution must be an acid. And because I have two bumps in the graph, it is polyprotic. D Chem 30 is done. Woo. All right. Okay, I hope this helps everybody. Good luck on your diploma.